All right, here we go for number 23. Okay, so the first thing I'm going to do is add my numerator. Adding and subtracting is the pickiest. So basically what's happening in my numerator is I'm going to describe how many square roots of the 9/5 that I have. So I have 9, and then my denominator. And what I'm actually going to do here is, if you guys notice, these are both square roots. So what I'm going to do is try to clean this up. And since they're both square roots, I can ignore the square roots and simplify the 9's within. So I'm going to subtract the exponents of 5 and 7. So when I get 5 minus 7, I get negative 2, which forces it to be in the denominator. And now I'm just going to bring that square root back. And this 9 that I wrote on top is the original 9 over here. But now what happens in the bottom is the square root of 9 squared is just 9. I get 9 over 9, and this ends up just being worth 1. Actually, a really simple problem. So, all right, 24. Let's take a look at 24. So on 24, what's going to happen is everything is going to have a perfect square root. So the 6 that's already out there, the square root of x squared is x, and that's going to happen on the second one. And then you're going to see the 81, and the square root of x to the 16th is just x to the 8th. And when I'm done, on top I have 6x squared, and on the bottom I have 81x to the 8th. And now I'm just going to simplify my fractions. With the 6 and the 81, I'm going to take a 3 out. And with my x's, I'm going to get 2 minus 8, which is a negative 6. But then that negative 6 says just move it to the bottom. And there's 24. All right, 25. Again, adding and subtracting is the pickiest of them all. So what I'm going to do is simplify these two problems. So first on the first term, the 32 is going to come all the way out because the cubed root of 32 is 2. It's going to join the y cubed that's there. And then the x to the fourth, nothing can be done with that. It's got to stay in there. Now when I go to my second term, none of the x can come out. But my y to the 15th has a perfect fifth root, so that can become y cubed. And now, when I'm ready to subtract them, it's how many of these y cubed fifth roots of x to the fourth is, and I have negative 5 of them. I'm going to kind of squish that 5 really close to the 3, so I'm actually going to put that in parentheses so they look separated. Okay, so there's 25. All right, going to the next page. 26. All right, starting on 26, all these A, B, C, D, E versions of it, this is where you might want to bring out your cheat sheet because of the rationalizing of the denominator. And there's a couple of different ways you can go about this. So the first time I go about this problem, I'm going to go about it more of using the cheat sheet. So as far as my 11s go, I don't like that fourth root in the denominator. So what I'm going to do is rationalize it. And actually, I'm looking at it now, and it might be easier just to, because the bases are 11, I'm going to change my process on this. I'm going to write them as exponents, 11 to the first, and then the bottom would be written as 11 to the 1/4. And then actually what I can do is just rewrite this as following the rules of exponents and make this 11 to the 3/4 power. And I'm only doing that because that is actually the fastest way to go through this. I don't have to rationalize the denominator, but this only works looking at the other problems on this one because the bases happen to be 11. So if you look online at the answer key that's emailed out, I don't use this method. I go about this much longer, and I didn't even realize about the 11s being the same until just now. So that's what I would do for 26A. 26B, I will not have to rationalize the denominator because looking at that y to the 8th, it's going to have a perfect fourth root. So the fourth root of y to the 8th is just y squared. And then as far as my numerator goes, 4 goes into 17 4 times, but I will have a remainder of 1 left over. And so there's 26b. And for 26c, It's the square roots inside square roots. So what I'm actually going to do is just ignore all the square roots to start with, and I'm going to simplify the fraction 32 over 72, and I'm going to take an 8 out of both of them. So when I do that, I get 4/9. Those each have their own perfect square root. So 2 and 3, but they're still in square roots because of the overall original larger square root that I'm rewriting in blue. And because of that square root in the bottom, I'm going to rationalize. So I'm going to take it with another square root. And the first number that I can turn 3 into that has a perfect square root is 9. And I can do that by taking 3 times 3 to get to that 9. And the top becomes the square root of 6. So when I'm done, I end up with the square root of 6 on top and 3 on the bottom. And there is number 26. Again, you guys, there's different ways you can go about these problems. My method is not necessarily the most efficient way. D, looking at D, the only issue I'm going to have here is I'm going to have to rationalize. I could take some of that x out in the denominator, but no matter what, I'm still going to have to rationalize. So I'm just going to go straight to rationalizing. So my goal is to build x to the 6th into an exponent that 5 can go into. And if I think about the numbers that 5 can go into, 5 can go perfectly into 5, 10, 15. So I'm going to pick the first number after 6 in that list of 5, 10, 15, but I'm going to pick the smallest number after 6, which is 10. And this is how many x's I need in the denominator. So I already have 6, I just need to get 4 more. And then now the denominator has a perfect fifth root, x to the 10th, which going into the answer space just becomes x squared in the denominator. And as far as the numerator goes, I can't combine those. One's outside of this fifth root, one's inside, so I'm just going to put them together like this. And then that's it for D. All right, E. On E, the issue I have is, again, rationalizing the denominator. So using my cheat sheet, I want to look to build 27 into the first number that does have a perfect fifth root. So when I look to the cheat sheet, and I'm actually going to jump to the cheat sheet just so, again, you guys can see what I'm doing. I'm looking to build 27 into a perfect number that does have a perfect fifth root. And I'm going to be turning it into 243. And so to get to 243, I'm going to have to take it times 9. So the bottom now has a perfect fifth root of 243, which when I go to my final answer just becomes 3. And then the numerator, since these are both fifth roots, I can just make into fifth root of 45. Okay, and there's E. All right, F. F is going to be pretty quick, and I do not have to rationalize because since they're both fourth roots, I can ignore the fourth root. Just take the 32 and divide it by 2 and get 16. And now the fourth root of 16 is 2. There's my final answer for F. All right, let's go to G. So G, again, I want to simplify as much as possible. First, what I'm going to do is clean up what's inside the square root, and then I'm going to take stuff out. So I'm going to leave the 20 and the 9 alone for now, even though 9 has a perfect square root. I'm going to clean up my x's, so I have an x squared on top. Y squared I can't do anything with, and z squared I can't do anything with. But now I'm going to take out what's perfect. So I can take out the 9, the x, and the y squared. So building up my answer on the outside, I have 3 in the denominator, an x and a y in the numerator. And now I'm going to break down the 20. I can break that down into 4 and 5. So the 4 is going to come out and join the x and y in the numerator spot. But what I still have is in a square root, I still have a 5 in the numerator, and I still have the z cubed. And I realize I wrote z squared there. I still have a z cubed in the denominator. And even though some of that z can come out, I'm still going to have to rationalize. So I'm just going to go straight to rationalizing. So again, I need to build z into having an exponent that the understood 2 that's there can go into an exponent. And so if I start looking at what 2 can go into, I want to pick the first number after 3 that's in this list of numbers that I'm writing down, but I want to pick the smallest number after 3, so 4. This is how many z's I need, and I have 3, so I'm going to add one more. And now the bottom is going to become the 3 that's there, the square root of z to the 4th, which as far as the bottom goes, then for my final answer, I get 3z squared. And then for the top, in my numerator, the 2 in the xy that were outside the square root, and then in the square root will go the 5 and the z. And there is G. All right, H. On H, I'm looking for perfect cubed roots. So again, I think what I'm going to do is clean up what's inside of there first, and then I'll start simplifying it. So I'm going to clean up the x's. So 81 and 8 are going to stay there. I'm going to end up with an x on top, a y on the bottom, and a z on the bottom. And now I'm looking to take out perfect cubed roots. So what's perfect at this point is the 8. It can come out and become a 2. The 81 I'm going to break down into 27 and 3, and the 27 can come out as a 3. But what's still left in a cube root is going to be the 3 and the x in the numerator, and the y and z in the denominator. So now what I'm going to have to do is rationalize that denominator. So rewriting it over here, because I've run out of room, is, again, I need to build this y and z into exponents that 3 can go into. And I have 1 of each so far. I need a total of 3, so I'm going to have to add 2 more of each. So y squared with the z squared on the top and on the bottom. And then when I go for my final answer in the denominator, I'm going to have the 2 that was there, and then inside my cubed root will now be perfect cubed roots of y cubed and z cubed. So I'm going to go up to the answer space now. When I take the cubed root, my denominator is going to be 2 with y and z in the denominator. And as far as the numerator goes, holy moly, I'm just going to combine this as much as I can. So the 3 is going to go along. And then in my cubed root, I will have a 3. And then I'm going to have the x, the y squared, and the z squared. And this is my answer. This looks no better, I think, than what we started with, but that's the rule and that's what they like. Okay? I'm going to try to finish up this page as much as I can in the next 2 minutes. So here we are adding, subtracting, multiplying in a composite function, and dealing with the domain. So first I'm going to subtract, so I'm subtracting g of x minus f of x. And since the subtraction is applying to the whole parentheses, I'm going to be adding the opposite. So in the first parentheses, add the opposite. And when I add the opposite to the whole parentheses, it becomes negative x cubed and then plus x squared. And then what will quickly happen are the x squareds will cancel out, and I'm going to write my answer in standard form as negative x cubed plus 3. I don't have any issues with the domain. It's going to be all real numbers. Remember, issues with the domains are with x's being in the denominator, x being in even roots, or both. So the next one, I'm going to multiply. So when I multiply, I'm actually going to start writing them in standard form. So there's f of x, and here's g of x. I've gone ahead and add the opposite, and now I'm going to distribute. First, I'm going to distribute the x cubed in. So when I do that, I get negative x to the 5th plus 3x cubed. And now I'm going to distribute the negative x squared. And when I do that, I get x to the 4th and negative 3x squared. Already I can see that my domain is going to be all real numbers, but now I'm just going to write my answer in standard form. So my answer in standard form is negative x to the 5th plus x to the 4th plus 3x cubed plus negative 3x squared. And that's it. That's all I can put into these 15 minutes. So I will pick up the other one in my next video segment.